Hello everyone, welcome to the 14th tutorial class on digital communication. In this class, we will discuss another digital modulation technique which is differential pulse shift keying or DPSK. During this class, we will also discuss about the generation detection and the corresponding bandwidth calculation for the DPSK, and at the end we will discuss some of the advantages and disadvantages of DPSK over the conventional PSK or BPSK. Now coming to the definition or the property of the DPSK. DPSK is basically non-coherent version of BPSK. That means non-coherent, which denote that in the receiver section we do not need any kind of reference or local oscillator. That means we don't need any kind of frequency synchronization at the receiver end. The reason behind this non-coherent version of BPSK that will be discussed in the upcoming slide. Now, formally we can say that DPSK is a combination of differential line coding and conventional binary phase shift key digital modulation technique. Okay, so differential line coding technique is combined with BPSK, and that will be nothing but the DPSK. You can see that this one is basically the differential line coding, where if the current bit is 1, then the shift will be occurred, else the voltage level will remain in the same level. Okay, so you can see that if you assume that initial 1 is denoted by plus a by 2, then the next term will be denoted by minus a by 2, and it will be continued. Okay, and you can see that for if there is 0, so previous voltage level will be continued. So whenever there is 1, the shift will be occur. So that is the differential line coding, where the shift in voltage level occur when there is 1 in the bit sequence. However, in case of DPSK, the digital information content in binary data is encoded in term of signal transition or phase shift. So the here the phase of the modulated signal will be shifted relative to the previous signal element bit. Okay, again the phase of the modulated signal will be shifted relative to the previous signal element. Okay, so uh, consider consider this one is the differential line coding. So similarly, if DPSK follow the same rule as this differential line coding, so here one will denote the transition in phase, whereas the bit 0 denote there is no transition. Okay, so in case of differential line coding, 1 denote the transition in voltage level. In case of DPSK, 1 denote transition in phase, and 0 denote there is no transition. Remember that in case of BPSK, there is two phase angle is possible. One is 0 and another is pi. So for one, uh, 0 phase angle, and for 0 the phase angle is pi. That means uh, the phase of for BPSK for the corresponding input bit are fixed, but in case of DPSK, this one, that means phase for 1 or 0 is not fixed. Let's discuss with the waveform to understand it more clarity. So this one is the some example of DPSK waveform. So consider a bit sequence of 001101000010 like this. Okay, so so for DPSK there is one rule, that means if the data is 1, then the phase of the signal will be reversed or shifted or changed as the differential line coding, and if the data bit is low, that is 0, then the phase of the signal will be not reversed, it will be continued or it will remain and as it was. Okay, so consider the first bit, for this example like 0 0. Okay, so consider suppose the initial phase is pi. So the modulated wave, it will be continued up to this, and as the next phase is 0, there will be no phase shift. That means it will be continued up to the next time period. Okay, now here you can see that as the next bit is 1, so obviously there will be some kind of phase shift. That means if for here for 0 the phase is pi, so obviously for the next one the phase will be reversed. That means here the phase is 0. Okay, so it will be continued up to for this time duration. Okay, now as the again next bit is 0, sorry 1, so obviously uh, the phase shift for the next one will be again pi. Okay, and for 0 again there is no change, so obviously this signal will be continued. So you can observe that for 0 the phase is 0, but here the for this 0 the phase is pi. Again for this one phase is 0, but for this one phase is pi. So obviously we can conclude that for 0 or 1 in case of DPSK, it can take either 0 or plus or pi. They can take both value, but depending on the previous bit. So if the previous bit sorry, if the current bit is 1, so obviously there will be no phase shift, and if the current bit is 0, sorry, if the current bit is 1, there will be phase shift, and if the current bit is 0, there will be no phase shift. Okay, so if you want to try, or if you want to express the DPSK in term of mathematical expression, that can be written as like this: st for DPSK, that will be plus minus root 2 ps cos 2 pi fc t. Why plus minus? Because um, uh, this value either for 1 or 0, they can take both uh, they can take both phase like 0 and pi. For 0 the amplitude will be plus a, and for pi the amplitude will be minus a, because cos 2 pi fct plus pi equal to minus a. So obviously for 0 and 1 both they can both take plus minus a. That's why written as like this: st dpsk is equal to plus minus root 2 ps into cos 2 pi fct. Okay, so this is the mathematical equation for dpsk, and this is where the this one is the waveform of DPSK. Remember, 1 means change, 0 means no change. Obviously, change in case of phase shift. Okay. So, coming to the next part, that is the generation of the DPSK. So, DPSK, as we already told, DPSK is the uh, non-coherent version of BPSK. Okay. So, here we don't need any kind of reference or phase signal. Okay. So, you can see that this one is the a block diagram of DPSK modulator. For a DPSK modulator, we need an encoder, a product modulator, and a time delay section. Consider BK is the input bit sequence. Okay. Now the it has been incident into the encoder section. The output of the encoder is DK. Okay. Now wo- one part of the DK is going to the time delay section. Okay, so obviously what will happen, the output of the time delay section will be dk minus 1. That means it will be shifted rightwards. Okay, now you can see that the output of the time delay will go again to the encoder section. So the input to the encoder is bk and dk minus 1, and the output is dk of encoder. Now output of the encoder, that is dk, is going to the product modulator, which where it is multiplied or modulated by the corresponding carrier ac into cos 2 pi fct. Okay, and after that we will get the corresponding differential phase shift key signal, that is nothing but plus minus ac cos 2 pi fct. Okay, so this one is the basic block diagram of DPSK modulator. Now, what is the function of the encoder and what is the necessity of time delay section, that will be understand in the next slide. So, already we have mentioned it, like DPSK encode two signal, the carrier and the modulating signal with 180 phase shift each. The serial data BK input is given to the encoder gate, and the output DK is again feedback to the other input through 1 bit delayed extra, that is DK minus 1. Okay. Now the output of the encoder along with the carrier signal is given to the balance modulator to produce the DPSK modulator. Now the encoder is either XOR gate or XNOR gate. Now, if you follow the rule that 1 denote the transition in phase and 0 denote no transition in phase, then encoder will be XOR gate. And if you follow the reverse rule, that is 1 denote the no transition and 0 denote transition in phase, so in that case encoder is nothing but an 2 input XNOR gate. So why do we conclude this XOR or XNOR gate as an encoder? That will be discussed in the upcoming slide. And moreover, it is worth to mention that again, like BPSK, the phase of 0 and 1 are not fixed. They can take both 0 and pi, but depending on the previous bit. Okay. So here, this is one is the example of DPSK encoding technique. Okay, and it will help you to understand DPSK with more clarity. So consider for this scenario, we'll consider the rule that 1 denotes the change in phase and 0 denotes no change in phase. Okay, so we'll follow this conventional rule throughout this presentation, okay, or throughout the class. Like consider the input bit sequence is BK, which is given by 0010010010011 like this. So imagine an arbitrary bit sequence, 00010010011. Okay, so our objective is to create a DPSK signal corresponding to this bit sequence. Okay, that means that is nothing but DK. Okay, now whenever we want to create the differential phase shift key, that means we need to first generate a differential bit sequence. Okay, so whenever we try to write that corresponding differential bit sequence, we need to use a reference bit level. So for this purpose sorry, for this purpose we use or we consider the initial bit or reference bit is 1. That's why it is marked as 1 asterisk. Okay, so so initial or reference bit is 1. Okay, now as we follow the rule that 0 means no change and 1 means change, so as the current input is 0, so obviously it will follow the previous bit, so obviously corresponding output of DK is 1. Okay, again next input is 0, so obviously it will follow the previous, so obviously it will be 1. Now coming to the next, as the next input is 1, so obviously voltage level or value will be inverted or reversed. So obviously this one, as the output is 1, previous output is 1, so obviously this one will be 0. Now 0 means no transition, so obviously no transition. 0 means no transition. Okay, now coming to the input is 1, so obviously 0 will become 1 and again 0, so 1 will be continued, 0, 1 will be continued, 1, that means 1 will be converted into 0, 1, 0 will be converted to 1. So ultimately we get the bit sequence like 1100011101 like this. Okay, now uh, so this one is the corresponding DK. Now, obviously, as we know that to generate the corresponding PSK, just we need to use a product modulator where the cos 2 pi fc has been used as the input, another input. So if we use the corresponding modulator, that means product modulator. So here there will be some kind of phase shift, and rule for the corresponding BPSK will be for 1 there will be no phase, 0 phase angle, and for 0 that will be pi phase shift, pi phase angle. So you can see that for 1 the corresponding phase is 0, for 1 corresponding 0 0, for 0 0 there is phase is pi, for 1 1 1, so corresponding phase is 0 0 0, for 0 pi 1, like this. Okay, so I think this one is the clear. So initially we create DK and then we create the corresponding phase of the DK using BBSK rule. Now coming to the DK minus 1, so this is nothing but if we shift this bit sequence one step rightwards, so that will be nothing but dk minus 1. So obviously one will be this one will be this one will be this one. That means total bit sequence that will be shifted by one position. So 1 1 1 0 0 0 1 1 1 0. Now again the phase of the corresponding dk minus 1 as per the bpsk rule, that means if we get, that means this bit sequence will be shifted rightwards, that means 0 0 0 pi 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 0 0 0 pi. Okay, so this one is the phase of dk minus 1 and this one the phase of dk. Okay, clear? So okay, now coming to the an interesting part. If you observe the bk dk and dk minus 1, then we can see that if we make xor between bk and dk minus 1, then we can get the ultimate dk. Okay, so the bit sequence, sorry, yeah, it is interesting to observe that the XOR operation between BK and DK minus 1 is DK. So we can write DK is nothing but BK XOR DK minus 1. So you can see where you can see that this one is the DK minus 1 and this one is, so you know that for XOR between 0 and 1, output will be 1. So 0 and 1, output is 1. So this one is the 0, this one is the 1, so output is 1. This one is the 1 and this one is the 1, so 1 XOR 1, that is 0, so obviously output is 0. 0 0 0 0 0 0 1 0 1 0 1 1 0 1 1 1 1 0 1 0 0 1. Okay, so obviously it follow the XOR rule. So we can write that dk equal to bk XOR dk minus 1. So by using this simple logic, we can easily construct DPSK modulator. So that's why we already mentioned that the encoder part is nothing but an XOR gate. Okay, so if we follow the rule that one denote the change, one denote the transition in phase, and 0 denotes no shift or no transition in phase. So if we follow that rule, so obviously encoder will be nothing but an XOR gate. Whereas if you follow the rule that 0 denote the change and 1 denotes no change, in that case we will find from this similar table that encoder will be nothing but an XOR gate, XNOR gate. Okay. Now coming to the next part, like if you want demodulator section. So suppose so we what we have a bk dk dk minus 1 and their corresponding phase of dk and phase of dk minus 1. Now if you make comparison between dk and dk minus 1, okay, if we compare the phase of dk and dk minus 1, so what we get? And if we make some kind of rule like that, that if there is phase difference, that means the phase of both signal are differ or not same, then corresponding output will be positive. And if their phase are same, that means there is no phase difference, that means phi is 0. So in that scenario the corresponding output will be the negative. So if we follow some kind of this rule, so we can let's see what will happen. So we want to compare the phase of dk and phase of dk minus 1. So you can see that the phase of dk, for the first case the phase of dk is 0 and the phase of dk minus 1 is 0. So obviously both there is no phase difference, so output will be obviously negative. So this one 0, this one 0, then both there are no phase difference, output will be negative. Here you can see that the phase of decay is pi, whereas phase of decay minus 1 is 0. So there is phase difference, so we will consider as positive. You can see here in both case of dk and dk minus 1, the phase is pi, so obviously there is no phase difference, so obviously we will consider it as a negative. So like this way, if we follow this same rule, we will get like negative negative positive negative negative positive negative negative positive positive, like this. Okay, so now if we get this kind of voltage like negative and positive, and after that if we make some kind of decision making device where we use some kind of threshold or threshold voltage level at 0. So if we consider, if we use that rule that if negative voltage we will consider it as 0, and if that is if we get the positive voltage we consider as 1. So ultimately we get that as the a bit sequence like this, like 0 0 1 0 0 1 0 0 1 1, where you can see that where there is positive we'll consider the 1, and where is negative we'll consider as 0. It is interesting to note that bk and this bit sequence are same. That means origin, that means this is nothing but detected bit. So ultimately what we get, the demodulated wave. So by using the logic we can create the demodulator of DPSK. So how can we create the demodulator section? So we need to know the phase of decay and phase of decay minus 1. We need to make compare between them, and after that we need somehow encode the corresponding phase difference in term of 0 and 1. So you can see that this one is the basic block diagram of demodulator section. So here you can see that there is a product modulator and integrator part, and next one is the design device. So this one is the incoming DPSK signal, which is nothing but decay. Okay, and it is going through a delay section. So ultimately, this one will be decay minus 1. And if both signal go to a product modulator part, and that is followed by an integrator section. So this product modulator and the integrated part will behave like phase comparator. Okay, so phase, ultimately what will get, the output of this integrator will be either positive or negative. Now if the value is positive, then we will consider as 1, and if the value is the negative, so at we'll consider as 0. Okay, so here this one is the decision making device, simple logic, and where we use threshold as the 0 volt voltage level. So this one is the simple DPSK demodulator. So this can be generated by using this simple table. Okay, so here also this one is the written as, one is the reference bit encoded as similar is the XOR gate, and comparison of decay and decay minus 1, same phase that is negative and defined phase positive. Clear? So this one is the DPSK demodulator part. By using the simple logic we can recover original 1 or 0 bit sequence. And you can see that here we don't use any kind of local oscillator carrier signal. We do not need to know the what is the value of FC here. We just use a product modulator, a delay section, and integrator to create the phase difference between them, and depending on the phase difference we make some kind of decision, either 1 or 0. Okay, so that's why you call it as the non-coherent BPSK version, where we don't need any kind of carrier signal. Okay, now coming to the bandwidth of DPSK. So as the corresponding mathematical equation for the DPSK is given by plus minus AC cos 2 pi FCT, so the corresponding PSD is the similar type of BPSK. However, it is interesting to know that in case of DPSK, the change occurs only when the corresponding bit level is 1, and there is no change only when the input is 0. Okay, so obviously you can conclude that one previous bit is always used to define the phase shift of next bit. Okay, so therefore the symbol can be said to have two bits. Okay, so one symbol duration is equivalent to here 2 bit duration, that is 2 into TB. Again I am saying that as the depending on the previous bit, the phase shift of the current bit will happen. Okay, so from by considering this logic, that one previous bit always needed. Okay, one previous bit is always used to define the phase shift of the next bit. That means if current previous phase shift is 180 or 0, so depending on that the current will be either 0 or 180. So if current is 1, so obviously there will be phase shift. Okay, and for 0 there will be no phase shift, but we need to know the previous bit. So for this reason we can say that one symbol consists of 2 bits. So for that reason we define the one symbol duration for the DPSK as the equivalent of 2 bit duration, that is 2 TB. So we can define 2 T, capital T, equal to 2 into TB. Okay, so bandwidth for the DPSK can be given by 2 by T, that is 1 by TB. Okay, if you substitute T equal to 2 TB, so we can get 1 by TB. So minimum bandwidth for the DPSK is FB, whereas the bandwidth requirement for the BPSK is 2 MB. Okay, so obviously this one is the advantage of DPSK. Now coming to the advantages and disadvantages of the DPSK. So you can see that first one is the DPSK is the purely non-coherent process. That means we don't need any kind of local oscillator or any kind of carrier at the receiver section. This one is the major advantages, major advantage. Okay, and second one is the bandwidth requirement. So bandwidth requirement of the DPSK is reduced by half if we consider the bandwidth requirement for the BPSK. Okay, and but there is some kind a huge disadvantage for that DPSK. So in case of DPSK, we already know that previous bit is used to detect the next bit. Okay, because depending on the previous bit, the corresponding phase shift will occur. Okay, it will be either 0 or 180, but that also depend on the previous bit. So if any error has been occurred in the previous bit, obviously the error will be continued in the next bit also. So obviously for one bit error at the receiver, for any kind of reason, we may get 2-bit error in the receiver section. So, so error is created in the next bit also. Therefore, there is tendency appearing error in pair in DPSK. That means for this reason, it will help to increase noise interference in case of DPSK, and it will also increase the probability of error for DPSK over the BPSK. Okay, because in case of BPSK, the current symbol is independent of the previous one, where 1 and 0 has the fixed phase shift. That means 1 is denoted by 0 phase shift, and 0 is defined by no phase angle. 0 is defined by pi phase angle. Okay, so here it it is independent of the previous bit. For that reason, only one bit can be erroneous. But whereas in case of DPSK, if any bit become erroneous, so that will help to become the next bit erroneous. So for that reason, we may conclude that DPSK is more has more tendency to become noise interfere, and it has more probability of error. So coming to the conclusion part, so in this class we have studied the DPSK, that is differential phase shifting type of digital modulation, which is combination of differential line coding and phase shift key. And we have already observed the corresponding waveform where one denoted by the phase shift in the waveform and 0 define the no phase shift in the waveform. But we should remember that the uh, phase of the for the current bit depending on the previous bit also. And moreover, apart from the waveform, we have also observed the generation and detection part, where we don't need any kind of um, coherent signal or carrier at the receiver end. And moreover, we have also observed that the PSK has the larger probability of error, okay, compared to the BPSK. So this one are the some references that we have used. Thank you. If you have any question, please post them.